Hello everyone. So today we're going to continue on 13.2. So if I remember correctly, in the last two videos, we get to talk about defining what is matrix exponential, which is defined by this expression right here. And we get to see one example on how to calculate matrix differential, which matrix exponential, which actually come out to be pretty straightforward for this one because of the fact that we have a diagonal matrix. And then we get to talk about properties of a matrix exponential, which surprisingly, it actually follow what we established for exponents. So that's extremely interesting. And of course, the most important property is this number 3 right here, where it tells us that when you take the derivative of a matrix exponential, it just simply equal to the matrix A times the matrix exponential, and which is kind of neat. And remember, when you see this, this is actually a matrix multiplication between two matrices. A is a matrix, e to ta is also a matrix, so keep that in mind. And last video we get to prove those properties. So now what we're going to try to do is to try to use it to solve a system. So remember, in order for it to be a solution to a system of differential equation, it must satisfy these two properties, which is the differential equation and the initial condition. And we can show that if we have the equation in the form of e to ta vector x sub 0, it will satisfy both conditions, the differential equation and the initial condition, which give us technically the solution to the system of differential equation. So what we're going to try to do today will be to go through some example using matrix exponential to try to solve a system of differential equation. So let's see if we can try this. So let's start with a very basic one. So here's our first example. Let's say we're given this is true. So let's try to use matrix exponential to solve this solve this initial value problem. All right. So it's actually pretty simple because we know the answer of this matrix exponential to this differential equation is the following. So we basically just let A equal to matrix 2, 0, 0, 3. Then we know that the solution must be this. Must be e to ta times vector x sub 0, which in this case vector x sub 0 is right here. This is basically what vector x sub 0 is. So therefore, this just equal to e to ta multiplied by 4, 5. So the question obviously would be to try to figure out what this is. Okay, which actually is not hard to do because we kind of already know what this is because we did that example up here. Right here. So we actually know the matrix exponential, but I'm just going to go through the process here and see if we can figure it out. Okay, because it's probably going to be just like that. So let's try to do this. Let's say we want to try to find this. So that's just basically the summation j from 0 to infinity t to the j over j factorial a to the j. So that's just the summation j from 0 to infinity t to j over j factorial 2, 0, 0, 3 to the j power. And based on what we learned up here in our example right here, let's look it up. When I have that, a to the j power just be 2 to j, 0, 0, 3 to the j. So that's important for us to move forward. So let's use that. So that just basically equal to summation j from 0 to infinity t to the j over j factorial 2 to the j, 0, 0, 3 to the j. And now what I'm going to do is I basically distribute the summation to the two the main diagonal, because I mean the other two are just 0, so therefore it's totally not relevant. So now how do we interpret what happened here? So actually pretty simple to interpret it. If you look at this right here, I'm going to just go from here. So that just basically means the summation j from 0 to infinity 2t to the j over j factorial. Because since t to the j power and 2 to the j power, and combine them together become 2t to the j. And so that plays the role of x in our exponential definition for e to the x. See, this is how we define e to x is x to the j power. So what we have is instead of x, we have 2t to the j. So therefore, actually maybe I should write it this way. I'm going to write it this way instead. I'm going to write 1 on top, and then we'll put 2t to the j. So you can see that this 2t actually plays the role of x. So therefore, that actually come out to be e to the 2t. And for similar reason, this will come out to be e to the 3t. Okay, maybe I'll write out the one extra step just to show you. Is that this will form summation j from 0 to infinity 1 over j factorial 3t to the j. And so that turned out to be e to 3t. So therefore tell me that e to ta, so therefore e to ta actually wound up being this matrix. So therefore, tell me that our answer, vector x, must equal to e to 2t, 0, 0, e to 3t, because that's e to ta, multiplied by 4, 5. So therefore, come out to the vector 4 e to 2t and 5 e to 3t. So that's our answer right there. Now the question comes down to, does it work? Well, let's find out. Let's check. So let's do a quick check. So if I have d vector x over dt equal to 2003 times xy, then that would tell me this just become 2x3y. That just tells me that that should equal to 8 e to 2t, 15 e to 3t. Let's see if that's the case. I'm going to go and take the derivative with respect of t of our vector x, which is 4 e to 2t and 5 e to 3t. And when I do that, I get 4 times 2 e to 2t and 5 times 3 e to 3t. And that come out to be 8 e to 2t and 15 e to 3t. Which is exactly what 2x 3y equal to. So that works out. Now what happens if I plug in 0? Well, if I plug in 0, I just get 4 e to 2 times 0 and 5 e to 3 times 0. And guess what? That is 4, 5. So it checked out. So that's the basic idea of how we go solve a initial value problem using matrix exponential. Is that we go find the matrix exponential, multiply by the initial condition, and then voila, we say we're done. Now, of course, then you probably realize that the most difficult part of the problem would actually be to find e to ta, which is true. So let's show a second example, which is a little harder to do. Okay. So let's see if we can figure this one out. So here's our next example. What if d vector x over dt is equal to 1, 1, 0, 1 times xy? And let's say we have an initial condition, x of 0 equal to 1, 3. So let's say we'll solve using matrix exponential. And I think some of you might be thinking like, can I solve it using eigenvalue, eigenvector? Absolutely. We're going to make a connection. Maybe not in today's video, but would be in our next video, where we're going to make a connection between matrix exponential with our eigenvalue and eigenvector. Now, of course, as I mentioned before, the more powerful things about matrix exponential is that it will still work even if you have a matrix with repeated eigenvalue. While if using the eigenvalue, eigenvector method, you will not be able to find the most general solution if you have a repeated eigenvalue. So that will be mainly the reason why we use matrix exponential. Okay, but we'll slowly work our way to that. So let's see if we can figure out what this is. So clearly here's our answer. Our answer will be this. The problem is we just have to find e to ta when a is 1, 1, 0, 1. So that's what we need to do. Once we figure that out, we can then put our answer together. So how are we going to do this? So at this stage, we really don't have anything that we know that we can do. So we just have to go with what we did before. We'll try to go through the power of A and see if we can find some kind of pattern. And then hopefully by using the pattern that we know, we can figure out what's going on. Okay? So I guess let's go for it and see what happens. So we know that A is 1, 1, 0, 1. So then what is A squared? Well, if you calculate A squared, that'll be 1, 1, 0, 1 multiplied by 1, 1, 0, 1. And that would come out to be 1, 1 times 1, 0, which is 1 plus 0, which is 1. 1, 1, dot product 1, 1 will be 1 plus 1, which is 2. 0, 1 times 1, 0 would actually become 0 plus 0, which is 0. And then 0, 1 times 1, 1 will be 0 plus 1, which is 1. So that's what A squared look like. Let's do A to the third. A to the third will technically be A squared times A. So I'm just going to do 1, 2, 0, 1 multiplied by 1, 1, 0, 1. And when I do that, I get 1, 2 times 1, 0, which is 1 plus 0, which is 1. 1, 2 dot product 1, 1 is 1 plus 2, which is 3. 0, 1 times 1, 0 would give you 0. And 0, 1 times 1, 1 would give you 0 plus 1, which is 1. So I see a pattern emerging, but I don't know for sure yet. I'm going to do one more just in case. And my next one would be A to 4, which is A to the third times A. And I have a suspicion as to what this should be. And I'm hoping that all of you looking at watching this video also have the same exact suspicion that I have. And now a question of whether it will be true or not. So let's find out. So that will be 1, 3, 0, 1 multiplied by 1, 1, 0, 1. So when I do the dot product, 1, 3 dot product 1, 0 is 1 plus 0, which is 1. 1, 3 dot product 1, 1 is 1 plus 3, which is 4. And then 0, 1. Notice that that is exactly what I expected. And I hope that's what you expected too. So therefore, I can now see that this pattern follow to this. A to J seem to give out 1, J, 0, 1. So A to first is 1, 1, 0, 1. And A to second is 1, 2, 0, 1. And A to third is 1, 3, 0, 1. A to 4 is 1, 4, 0, 1. So it makes sense that for me to say that A to J will be 1, J, 0, 1. So now the question is, how does that impact our matrix exponential? Well, let's find out. So now I'm going to try to do is try to find out what is e to ta going to be. So that's come out to be summation j from 0 to infinity t to the j over j factorial a to the j. So we're going to go through the same exact thing just like what we did on the last example. That's j from 0 to infinity, t to the j over j factorial, multiplied by the matrix 1, j, 0, 1. So what I'm going to do is I'm going to now distribute the summation to all of them. So therefore it's summation j from 0 to infinity, t to j over j factorial, j times t. Oh, actually, no. The j would have to be inside. So the inside would be summation j from 0 to infinity, t to the j over j factorial times j. This one will be 0 regardless what we do. This one will be j from 0 to infinity, t to the j over j factorial. So now it's just a matter of figuring out what all these summation actually converges to. So first I notice that these two will just directly converges to e to the t. Okay, because that's basically what the definition of the exponential function is, except I changed the letter x to letter t, so therefore it becomes e to the t instead of e to the x. The tricky part is what happened to this one right here. So this is the one that we kind of not sure what's happening because of an extra j there. So what we're going to try to do is try to figure out how that works. So what I'm going to do is I'm going to kind of pull it out and just take a look at right here by itself. So that will be summation j from 0 to infinity, t to the j over j factorial times j. So clearly what happened is that that j would cancel the j factorial on the bottom and therefore result in j minus 1 factorial on the bottom. So that's what this becomes. And because to j minus 1, what happened is that's now becoming slight issues here. And that issue is that now the bottom become, if I plug in j equal to 0, then that would actually kind of ruin that become j minus 1 to become negative 1 power. So that's not going to work. So what I'm going to do is try to do the following. Okay, what I'm going to do is this. I'm going to break down the top t to j as t times t to j minus 1 power. And pull out the t out of our summation. And actually start my summation by discarding the first term, which doesn't make sense because I can't have negative 1 factorial. And now the question comes down to what does this summation turn into? Well, that summation just technically turn into e to the t. And if you're thinking like, wait, why does it turn to e to t? What I urge you to do is to actually write out the summation by expanding it. And then you'll see that it actually formed the same exact power series as e to the t. And the short answer to that is that this can be rewritten into j start from 0 and then just become j factorial and t to the j. Because notice that if j is equal 1, then we start 0 factorial and 0 power. So that's pretty much the short answer to that. So notice that that becomes e to t, but I do have a t in front. So therefore tell me that this thing actually turned to t e to t. And that gives us our matrix exponential. And surprise, surprise, if you think about it, does it make sense to have a t equal to t? Actually, it makes perfect sense because if you think about this matrix, matrix A right here, notice that this matrix A actually have a repeated eigenvalue of 1. If you don't believe me, you can try that out. And then you see, then that makes sense that to have a term that say t to t because of a repeated eigenvalue. But of course, it's not as simple as that, but it makes sense to have that term. So now I can actually put in my answer now. My answer would actually be this. So therefore, tell me that vector x will equal e to ta, vector x sub 0. And in this case, our vector x sub 0 is 1, 3. So therefore we come e to t, e to t 0, e to t multiplied by 1, 3. So therefore vector x would equal to e to t plus 3t e to t, and then 3 e to t. I'll leave it up to you to verify that this would work, and I assure you that it should. All right. I probably have time for one more example, so I'm going to go ahead and do one last example. So this one will be a little harder because we will actually get into complex. So what if I tell you that d vector x over dt equal to I, 0, 0, negative I, xy, with vector x of 0 equal to 1, 2. Then once again, the direction is solved by matrix exponential. So matrix exponential, this kind of shine compared to eigenvalue, eigenvector method, because when you have a complex matrix, you're likely to have complex eigenvalue, and therefore could result in complex eigenvector, and complex eigenvector is just hard to work with. So this actually might wind up being a little bit better. So show you what happened. So let's say, once again, the first thing is that we know that the answer that we're looking for is this. I try to figure out what e to ta is. Okay, and to do that, I will need to kind of figure out what a to the power is. So we'll just basically do the same thing here. So if a is equal to I, 0, 0, negative I, then what is a squared going to be? Well, that would be just I, 0, 0, negative I, multiplied by I, 0, 0, negative I. And some of you probably already figured out what that is because of what I told you about diagonal matrix. So that just basically comes out to be I times I, which is I squared, 0, 0, I squared. Well, technically negative I squared. Which basically come out to be negative 1, 0, 0, negative 1. And then what is a to the third? Well, a to the third is negative 1, 0, 0, negative 1, multiplied by I, 0, 0, negative I. That come out to be negative I, 0, 0, I. And guess what? That is technically I to the third, 0, 0, negative I to the third. And yes, it shouldn't be a surprise that this pattern continue. A to j power actually turn out to be I to the j power 0, 0, negative I, parentheses to the j power. And is that such a shocker? No, because that's what we figure out with this diagonal matrix. Okay. So now I'm ready to form my matrix exponential. So e to ta would equal to summation j from 0 to infinity, t to j over j factorial, multiplied by a to j. So that's summation j from 0 to infinity, t to j over j factorial. Matrix I to j, 0, 0, negative I, parenthesis to the j. So what does that turn into? Well, that turns into this. Summation j from 0 to infinity, t to the j over j factorial, multiplied by I to the j, 0, 0, summation j from 0 to infinity, t to j over j factorial, negative I to the j. That's the I, another one. Now, take a wild guess as to what these two things come up with based on what you see in this example. Notice that when you have 2 to the j and 3 to the j, when you form this summation, it actually turns to e to 2t, e to 3t. So it shouldn't come as a surprise that this thing right here would actually turn into converges to e to the it. And then this right here would convert into e to negative it. And yes, they form conjugate pair as they should with complex complex value here. So now I can say what vector x is. So vector x would equal to e to ta vector x sub 0. That's e to it 0, 0, e to negative it multiplied by 1, 2. So therefore come out to be e to it 2 e to negative it. Oops, negative it. And therefore come out to be following. So that becomes e to 0 plus I times t. So therefore be e to 0, which is 1, and then cosine 1t plus I sine 1t. And this one have a 2 in front, so become 2 cosine t, but minus 2I sine t. Because of the negative, that turned that into negative. And so that become my answers. All right. I think I'll stop right here. So that's 3 examples right here for you. I do believe that should be enough for this video, and we'll continue some more on the next video. All right, talk to you guys later. Bye bye.